teacher, y couldn't be inverse cube or any other power, and this is where we first encounter an explanation. So fields is the origin of force. And then the next thing I said was that there was this connection between the concept of field, particle, and force, and this is one of the most profound development in the history of physics. So this is all a review of yesterday, but as Professor Johnson just emphasized, it is very important to ask questions. And there was a professor named Herbert Bernstein in the United States, and he's much older than I am, and there are, in fact, people in the world older than I am. And he told me that I first went to the United States as a poor Chinese kid from Brazil, and I attended a summer school just much like this, and Herbert Bernstein, who now came back to the ITP, and in fact as what is called an ITP scholar, and he was under my supervision. I was supposed to supervise him, even though he was older. And he told me that I first came to his notice and came to the notice of all the other lecturers in the school because who is this Chinese kid? He asked all the questions and wouldn't let any of the lecturers at peace. So I still do that. And if I learn to laugh like Professor Maroff, then my life will be complete. So yesterday I mentioned that there's this very beautiful thing that each time we add a unit of spin, a Lorentz index to the field, we change the sign of the force between two external lumps. When we had a scalar field, we have an attraction, and Yukawa realizes that this could lead to an explanation of the force in the nucleus between protons and neutrons, and this led him to be awarded the Nobel Prize. And then we added a Lorentz index, and we have a vector field, and then we discover that the vector field provides a repulsion between like charges. And then we could go on, as we said, and add another index, and this becomes the gravitational field, and very naturally, this produces an attraction and the law of universal gravitation. And it's really a marvel, and every time I think about it, I still think it's absolutely marvelous how the universe is put together. It's this web of forces, the strong, the electromagnetic, and the gravitational force. They each have their own characteristics. Some are repulsive, some attractive, some long range, some short range. And altogether, they produce the universe as we know it. And some of this was described by Professor Ellis in his lectures. And finally, to complete the review, another thing we did was that when we did the scalar field, we started out with this Lagrangian that we kind of guessed. And we wrote down the Lagrangian. We didn't even know that it contains a particle. But we discovered it contains a particle by putting in sources and sinks, as Schwinger taught us to do. And we discovered that it has mass m, that it has spin 0, and then we discovered this particle, when it's exchanged, produced a force. So now, what we also asked was whether we can go backwards. So in the case of the spin 1 particle, I did it for you the other way. I assume that there's a particle of spin 1, and I use very general arguments to determine what its propagator looks like. And once I determine the propagator, we can actually go back and find the Lagrangian. We didn't start with the Lagrangian. And so in this way, also in my opinion, very beautiful. I can say it's very beautiful because this is not my work, of course. It's the work of the pioneers of quantum field theory. It's absolutely beautiful that we managed to find the Maxwell's Lagrangian with an extra mass term. So because the particle we started out with, we put in mass, but if we had, we can now at this point, we can set the mass equals to 0. So we actually discover Maxwell's Lagrangian, okay? So I want the students here, as Professor Clifford was saying, to feel the sense of excitement and beauty and amazement. You know, people should be amazed. You know, when you see this, people jump up for joy, you know, when the early days of quantum field theory. But instead, it's not to just sit there and sort of, okay? So now, so that was a review from yesterday's talk. Let me ask if there are any questions that specifically relate to the material in yesterday's talk. Yeah?
Is there any obvious way you can explain why the number of Lorentz indices gives the spin?
Well, it's as I explained, every time you introduce an extra spin in the metric, you go through this calculation. You introduce the polarization vector, and you have to go through the calculation, right? The calculation for the spin 1 case was displayed on one transparency. I was able to squeeze it all in one transparency. There was a minus sign. Yesterday, I went through this extremely carefully. I don't know what else I can do for you. I mean, I can go through the arithmetic step by step. But do you mean there's some intuitive way of... intuition often comes from experience. Like yesterday when I did this, Professor Marov said it was obvious to him that every time you add a spin, you'll change the sign. But that's because he has years of experience. So intuition is sometimes misleading. Maybe he has an intuitive answer. Oh, okay. Well, maybe he's smarter than you are. He said it was obvious afterwards. No, intuition sometimes also comes from experience, right? When you have seen this and dealt with this and so on and so forth. So I think it's one of those profound. To me, it's, yesterday I said I like to make top 10 lists of everything. So this certainly is sort of part of my top 10 in physics.
Something else that might be interesting. Why
yes.
Did you stop at spin 2?
Yeah. Okay. So the notion of you can keep on going to higher spins, and in the early days of quantum field theory, people did study higher spin theories, and it turns out that you can write them down. But there are two reasons why the study of higher spin fields stopped. One is that experimentally, they're typically not seen, or if they're seen, they're particles that decay very rapidly. They're not elementary particles. They don't seem to be fundamental. But there's even more profound reason, which of course I probably won't have time to get to within 4-lecture course on quantum field theory, which is a notion called renormalizability. You have to, yesterday, as I said, in answer to a question, we have to introduce a cutoff. The cutoff is absolutely physical. It's not some mathematical trick, as some of the older books would say. It's the cutoff, just a parameter of our ignorance of high-energy physics. But what we would like is that the things we calculate should not depend on our ignorance, right? Because if it depends on our ignorance, physics cannot make progress. So it turns out if you introduce the higher spin fields, the things would depend on the cutoff. So the theory, to use the technical jargon, becomes non-renormalizable, and that's why people stop at spin 2. And even spin 2, as you know, encounters lots and lots of difficulties within quantum field theory, and that is why some people have to invent a cure, and the people, it's like the believers, the true believers, think that string theory provides a cure, but the verdict remains out. Okay. Yes?
One more question. I have one question. That was when you wrote down the green function or the propagator.
Yes.
You had the I epsilon in there, and you didn't want to go into great detail. But can you just give a brief statement on why that has to do with causality?
Yeah. No, that's a good question. So when I introduced the Gaussian integral, in order to make it well-defined, to make it easy, I write it without an I here, exponential, because then this is absolutely well-defined, this Gaussian function, just some real function that decays to 0 infinity. But when you actually do quantum field theory in space-time, the functional integral has an I in it. And so it's still well-defined, but mathematically you need to go through some more steps, which it's just for lack of time. If I were teaching, I'm trying to teach quantum field theory in 4 lectures, so there are a lot of details I have to omit. Now, if you went to Professor Douglas Smith's lecture, you remember he puts an I and he does stationary phase. So I do steepest descent. But these are the kind of details that we just cannot go into in 4 lectures. Okay? Well, anyway, Professor Marov promised to explain Euclidean theory of gravity, he said in his first lecture or something.
But I
So that kind of details, I just have to refer you to a textbook. Okay, as I said, some of the things in yesterday's lecture, some of the things I squeezed under one transparency. Each transparency corresponds to a whole chapter, so there's just no way. Other questions? These are all valid questions, so please feel free to ask questions. Okay, now I want to come to a very important point, which you may realize, which is that we started out with this thing that I call picturesquely a matrix. Okay, so then the matrix represents the field. The excitations on the matrix are the fields, and so on. But then we took the harmonic approximation in order to make it so that we can do the calculation. And then we introduce external lumps. So these are external objects, and they sit on the matrix. And there is the field generates an interaction between these two external objects. So the external objects are interacting, but the excitations themselves, which is the field itself, is still not interacting. Okay, so this is an important point, so let me say it again. The external objects, what I call the lumps that we introduced, they interact. So they interact via the exchange of the scalar field phi. But the scalar field phi itself is not interacting, right? Because remember in the first lecture, I said you have to introduce n harmonic terms in order for the scalar fields to interact. Okay, and we drop this term. Okay, and the reason we drop this term is because then we can do the integral. The integral is then Gaussian. Okay, so now if we want to have the field interacting, we're going to one higher step of sophistication. We now go to interacting field theory. Okay, is that clear? Students sometimes get confused between, there are two kinds of objects here, which are interacting and not interacting. Where's the stick again? Oh, okay. Okay, the external objects are interacting because of the field phi, but the field phi itself is not interacting. To make the field phi interacting, we have to add some non-harmonic term. And this is the simplest possibility, okay? So it's not just why do I add a phi 4 and phi 6 and some other. This is just the simplest possibility. Then immediately the functional integral is no longer doable, okay? Because it's no longer Gaussian. So how do you do this integral? Now, this problem, as I said, is unsolved problem. I mean, students sometimes see this integral. They say, okay, go home and do the integral. Right? If you go home the integral, I nominate you for the Nobel Prize. Okay, so in my book, also as I developed this subject in the first lecture, I said that we have quantum field theory is one big functional integral, but on the other hand, in my attempt to make it sound simple to you, I say it's a continuum of problems. The functional integral, if we make it easier, then we just integral over a function of one variable. That's quantum mechanics, which some of you know. And then if you go one step below, then it's just an ordinary integral. And if you make you can be a multiple integral or just a single integral. So this is the real problem that we have to do. In my book, I introduced a child problem. The child problem in which is that instead of a field phi, which is a function of space-time, we now just have a vector, q. So q is just a vector with q1 through qn, so just a multiple integral. And then this differential operator becomes a matrix. You remember all this. Except now we have this extra term. So again, we cannot do the integral. And finally, let's reduce further. This is in the spirit of Einstein and Sam Edwards. I told you Einstein said physics should be as simple as possible, but not any simpler. And Sam Edwards said, if you have a problem you cannot do, you can keep making it more and more trivial until it becomes trivial. And then you go back one step. Okay, and students always have do the opposite of Sam Edwards. If they're given a complicated problem, they always make it twice as complicated, it's 3 times more complicated, and come back and said they can't do it. And so this is the baby problem. Okay, we cannot do this. We consider doing this. And this even we cannot do. If you can do this integral exactly, that would also be news. It would be entered into the table of integrals. Now, also as I explained them in the first lecture of this course, this guy, Mr. Feynman, had a brilliant idea, absolutely brilliant idea, worth a Nobel Prize. So I emphasize to you that all these brilliant ideas, in hindsight, it looks very simple. But the point is that you have to come up with them at the time. Okay. The brilliant idea is the following. Look at this integral. Since we can, this is a misprint. Since we could do all these problems, or we could evaluate all these integrals for lambda equal to 0, we ought to be able to do them in the limit as lambda goes to 0, right? Because all we do, the brilliant idea is to expand this as a series in lambda, which I can always do. This is just some exponential of lambda Q4. I can expand it in a series, and then I keep track of the many, many terms. There will be an infinite number of terms, and then I keep track of the terms by drawing little diagrams. So this is, again, one of the most brilliant ideas in the history of physics, and these diagrams are called Feynman diagram. Okay. So in my book, I do these integrals in detail, and again, it's one great long chapter, and when I gave a real course in Santa Barbara, we spent weeks going through these, but here, you have to be correspondingly much faster in absorbing information. We'll do it in 2 minutes. Okay, so this is quantum field theory. It's too hard. It's like Goldilocks and the three bears. This is too hard, and maybe this integral is too easy for you guys who are very sophisticated. So I'm going to do this intermediate problem, which is just right. So we'll do the child's problem. Okay, so here's the integral, and here's a famous quote by Anonymous. It is not a big deal. Okay, so it's just a multiple integral, as could be assigned in a course on calculus, as I kept saying, if I were teaching a course in calculus, right? It's just an integral. Look at this. I mean, people from their first, some of the students here are very overwhelmed, but look, this is just an integral over n variables, okay, with an n harmonic term and a ji, qi. Okay, in fact, we can do a double series expansion in j and lambda. We can just expand out this mess in the exponential. And I think Professor Smith, in his lectures, did a little bit of that already. Okay, so let me just give you an example. For example, if I pick out the terms quartic in j, suppose I just expand this term, and I only look at the term with 4 powers of j. Now remember, I explained that the j corresponds to sources and sinks. They produce and absorb the particles in a field theory. Okay? So, in the j's, I'm allowed to choose them to be any function in space-time, so I can localize them in space-time, which in this case means I can choose the dependence of I arbitrarily. However they depend on I can choose. This is just an external thing for me to choose. I'm completely free to choose what this external thing is. Okay? So therefore, if I choose the term that's quartic in j with 4 powers of j, it looks like this. So therefore, it looks exactly like since I told you each one of these is a source or sink, it produces 2 particles which then do something. They interact, and then they get reabsorbed. So in fact, we are talking about particle powdering, particle scattering. So all we have to do, if we want to study particle-particle scattering in quantum field theory, is to extract the coefficient of JA, JB, JC, JD. And A, B, C, D are then the location in space-time. Now you remember when we started out the matrix, this index I just tells me which of the mass point on the matrix we're talking about. Okay, so this A, B, C, D, just a point here, a point there, a point there, and a point there. Okay, so then we would immediately pick out the term for particle-particle scattering. So let me ask if there are any questions. Okay, so again, I emphasize I think this is probably the most important thing to keep in mind when you study advanced physics. At least I try to keep it in mind. It is not a big deal. This is very important. Probably one of the most important things that I would convey to you in this class. I see Professor Marov nodding his head. He doesn't think it's a big deal. So, okay. So if I extract the coefficient JA, JB, JC, JD here, we see that that gives me a term QA, QB, QC, QD, right? So, okay, if I take this and expand, I get QA, QB, QC, QD. And now I can expand in powers of lambda, as I said. We're doing a double expansion. So if I expand in powers of lambda, this is in the exponential. So we all know how to do that. There's a sum over p minus lambda over 4 to p, and then sum over qi to the 4p power, right? So now you know how to do this integral, as I've shown you, to any power in lambda. So if you want to make p equal to 17, fine. Then there's just a whole bunch of q's, right, from here, lots and lots of q's, and then qa, qb, qc, qd. So for any value of p, you can do this integral. And the way to do this integral, as I explained to you, is to just apply Wick contraction. So remember Mr. Wick's brilliant idea, right? So all you do is to draw lines contracting these q's, as I explained. And then you get, each time you connect two lines, for example, if I connect I to A, I would get the inverse of the matrix AI, IA, AI, J, B, and so on. If I connect J to D, I would get inverse JD. And I'm going to sum over all possible Wick contractions. So A is this matrix that appears in the integral, and we get the inverse. So the inverse is what we call the propagator. So all we are doing is multiply a bunch of propagators together, sum over them. Sum just means we write down all possibilities. So each term in this sum, we can draw a little picture, and that's the Feynman diagram. Okay? So if you follow my previous lectures, you should have no trouble doing this. So when I taught this course in Santa Barbara, what I told students to do is that they should just go home and do this integral. And I also told students here, after the second lecture, to go home and do this integral, but I don't know how many people actually did it. Okay, so if you cannot do this integral, this is what I call the child problem, then go back and do the baby problem. If you master the baby problem, I guarantee you that you understand Feynman diagrams. Okay, any questions? Okay. Okay, so it's really very, very simple. And as I said in my first lecture, Schwinger made a remark that after this, any idiot can do quantum field theory because you just follow Feynman's rules. So he said so Feynman said, we don't have to go through these steps every time. We can automate this process and, in fact, make a machine do it. And, in fact, now we can, in fact, make machines do it. When Feynman thought of something like that, it was, before the age of computers. But now we have computers. Machines can, in fact, do Feynman diagrams. So we just automate this process by counting down some rules. And these rules are called Feynman rules. And that's basically all there is to it for perturbative field theory. Now, remember what I said about perturbative field theory in my first lecture was you expand in the n-harmonicity. There are phenomena in quantum field theory, as I also said in the first lecture, that you cannot get at by using Feynman diagrams. And the revolution, one of the revolutions in the 1970s, was that we broke the shackles of Feynman diagrams. We throw Feynman diagrams out. Some people threw Feynman diagrams out the window. Okay? So that's basically all there is to it, to quantum field theory, to perturbative quantum field theory. Honestly, that's it. Okay? So it's even worse than what Schwinger said, right? Schwinger said after this Feynman guy wrote down these rules, any idiot can do quantum field theory. So now it's even worse than that. Not only any idiots, but any machines can do Feynman diagrams. Okay? So I just want, again, the theme of my lectures, and I think it's very important when you study physics, is to remember it is not a big deal. That there are people that are like you and me. Maybe they're a little bit smarter, like Feynman. When they're 20 years old, they come up with all this stuff. So you can understand this. There's no reason. Okay, it's very simple. Okay, now, of course, I've given this extremely simplified development on quantum field theory. And we can, of course, and people do. And remember, it has been 75 years. And human beings, like monkeys, like to keep busy. They do all kinds of little things. So there are all these people called physicists, So for 75 years, they've been playing with this thing. And so people have put in, during this last 75 years, lots of elaborations, and they attach bells and whistles to all the things I said, make it more complicated, and so on. But in essence, this is quantum field theory. Okay?
Can I ask a
Yes.
question someone asked me
Sure.
yesterday? Is there still research to be done on quantum field theory per se, as opposed to its applications to particle physics?
I'm a physicist. Well, the correct answer to this question is, of course, I am a physicist and not a prophet. And one of the students here, maybe you, tomorrow can come up with a brilliant breakthrough in quantum field theory. And so I hope that the answer to Professor Ellis's question is no, that there is still great things to be done in quantum field theory. And in the conclusion of my book, the concluding remarks is in fact an answer to this question. And I even suggest various things that can be done. So I certainly hope so. And you can also think of string theory as just a branch of quantum field theory, as I explained in the first lecture. You know, if you can solve 1 + 1 dimensional field theory, you're on your way to solving string theory. Yeah.
I think, well, to add to what you say, certainly in the area of, there's a lot of activity in research in quantum field theory and trying to understand non-potential issues. Issues that mean that you're beyond being able to get access to things that you want to calculate by using Feynman diagram. And that parameter isn't small. The theory presumably still makes sense, but you need techniques to calculate things. And so people come up with all kinds of clever methods for trying to calculate beyond perturbation theory. And also, it's not just a matter of finding tools. You also get to ask the question, what does it actually mean? What does the field theory mean when you're not doing perturbation theory? Can you still describe things in terms of individual particles with some nice weak interaction between them? Or do you need to completely rethink what's going on, what this Lagrangian is trying to tell you in the field theory? So that I think there are many deep questions which people don't know the answer to in quantum field theory, and there's a lot of research that's considered very exciting in these areas.
I absolutely agree with Clifford Johnson. What Professor Johnson said should encourage the young people. And I also touched upon this in my first lecture. You remember in the first lecture, which was a colloquium that I've given in various places, that I said once we broke the shackles of Feynman diagrams and threw Feynman out the window, we learned all kinds of wonderful things about quantum field theory, that you could be calculating Feynman diagrams till you're blue in the face. See, in an earlier generation, when I came along as a student, there are people walking around who have been calculating Feynman diagrams for 20 years and who intend to do it until they die. And these people would never discover all the wonderful things that were discovered. So I mentioned that some of the things that were discovered were magnetic monopoles by 't Hooft and Polyakov. They're dualities in quantum field theory, and the whole notion of duality was later applied to string theory. It turns out certain quantum field theories in strong coupling, when that parameter lambda is very big, so you cannot perturb, these properties are related to other field theories in which the coupling is small, and so on. So that I personally believe, in answer to Professor Ellis's question, there are all kinds of things to be discovered. But how can we say, right? We don't really know. We cannot. So it all depends on the young people, whether they are awake or asleep. Okay, yes, question.
Yes, little bit of trepidation of this question, because I've done neither field theory ever, nor general relativity, so I'm probably missing something obvious. Has field theory ever been applied to gravitation?
Oh, absolutely.
Has it? Okay.
Yeah. No, and in fact, if you like, yesterday we already touched upon that because we talked about spin 2 field. And so Einstein's theory of gravity is, in fact, if you like, a quantum field theory of a spin 2 field. Okay, although it has difficulties and so on. I don't know. I may be able to touch upon that in my next lecture, but I'm not sure. But it's okay. But that's a good question. So in fact, it's in the next in some sense, your questions about its elaborations and attaching bells and whistles. So in fact, we have already attached some bells and whistles we've attached Lorentz indices to the basic fields, and we attach one Lorentz index, we discover electromagnetism, and when we attach two indices, we discover gravity. So the answer to your question is yes, Einstein's theory can be thought of as a field theory, quantum field theory of a spin-2 field. Okay, and then there's also another very important development. Instead of adding Lorentz indices, there's another kind of index in mathematics, and it's called a spinor index. And so Paul Dirac, of course, in his brilliant remark, he added a spinor index alpha to describe a spin half field. And this is very important because all known matter fields, quarks and leptons, carry spin 1/2. And in Dirac's time, the spin 1/2 field, of course, was the electron. So we can develop quantum field theory of the spin half field along exactly the same line that I described for you for the spin 0 field. It's just more complicated. There's some index, extra index lying around. But otherwise, conceptually, it's easy. And this is done in part 2 of my book. I more or less even managed to cover part 1 of my book. Okay. So then the next step is to allow a spin 1/2 field, namely the electron, to interact with a spin 1 field, the photon, and this leads to quantum electrodynamics, okay, the quantum field theory of the photon and the electron. So far we have a very impoverished, as I call it, the discount store, bargain basement field theory. We have this scalar field with no indices, and it just interacts with itself. But we can introduce a field theory with all kinds of indices and have the different fields interact with each other, namely the photon with the electron, and that gives quantum electrodynamics. And one of the greatest triumphs of the human mind in the entire history of the race is, of course, Schwinger's calculation of the anomalous magnetic moment of the electron. Once you let the electron and photon interact, you can calculate the magnetic moment of the electron and to so many decimal places, and people are still doing that. Okay, are there any questions? Okay, so as I said on the first day, my plan was to, in the first lecture, give a very rough overview of quantum field theory from beginning to end, and then in the next lecture, develop scalar field theory, and then a little bit of spin 1 field theory, and allude to spin 1/2, and so on. And then I said that I only prepared transparencies for these, so much transparencies because I have to wait until I didn't know what kind of pace I would be going at, and I also wanted to see how things go, what the reactions from the students are. So, and then I told you my plan was then for the remaining time, I was going to, depending on how things go, discuss various topics, and I was not going to decide on which topics to do until I finish all the transparencies. So I have decided from how things go. So my next topic would be symmetry. So I'm going to just teach from my book. And I was going to tell the story about Dirac, but Professor Ellis already told the story yesterday. Which is when Professor Dirac announced that he was giving a course on quantum mechanics. Everybody got very excited. Everybody signed up for the course. And Professor Dirac just sat down, opened his book to page 1, and started reading. And when the students complained, he said, well, I put a lot of thoughts and effort into writing this book, making it as clear as possible, and it could not be improved upon. So I could do exactly and say exactly the same thing as Dirac. So chapter 1.9, symmetry.
Sorry to interrupt. Do you know the story about the letter as well?
No, I don't know the story about the letter.
I've forgotten exactly what the subject was, but someone wrote a letter to Dirac asking about, in section so-and-so of your book, you're not very clear about this particular point. Could you explain a little bit more? And you can then read the copy of the letter he sent back, and it's this clear explanation of this particular topic. And then actually, if you look and you go and you read it, he's just copied out what he wrote in the book.
Right. 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 So there are, of course, many Dirac stories, but I won't take up time. But if at the tea break you guys ask me, I can tell you many Dirac stories. The other famous one along the same line is, of course, during a seminar that Dirac was giving, somebody in the audience and raised his hand and said, "Professor Dirac, I do not understand what you just said." And Dirac said, "That is not a question, it's an assertion." No, right. So the importance of symmetry in modern physics cannot be overstated. When a law of physics does not change upon some transformation, that law is said to exhibit a symmetry. Okay, I won't do that. I won't do what Dirac did. I actually lecture on the board. So when we wrote down a quantum field theory, we already used the notion of symmetry, and namely that when we wrote down Lagrangian for the scalar field theory, we already used Lorentz invariance, right? So that, you remember, restricted the form of the derivative terms, and in particular the spatial derivative term and the time derivative terms are related. Now, the other thing that you may have noticed, it's for simplicity, I did not write down a phi cube term a few minutes ago. I only have a phi 4 term, and that's because I can do this by imposing a symmetry. Phi goes into minus phi. Okay? So there are these so I've already implicitly used the notion of symmetry. So if I introduce a phi without the phi 4 term, you remember that we have the interaction looks like this, right? That 4 particles can interact. But so the number of particles is always, so this particle, for example, can go like this. So this is another Feynman diagram. So this will be a process in which 2 particles could go into 4 particles. So you see the number of particles is always conserved, mod 2. But if I introduce a phi cube term, then that is no longer true because there will be diagrams like this. Okay. Now, we can, now that we've understood one scalar field, we can also introduce 2 scalar fields. So what if we just write down 2 scalar fields? So we can have a Lagrangian. Like this, right? So this would be a scalar field that we have studied, a scalar field theory. But now suppose we introduce 2 scalar fields. That's why I introduced the index 1. Suppose we have a field phi 1, but we also have a field phi 2. Okay? So we can write down the same thing. Phi 2, 4. Okay, very easy. We just change all the index phi 1 to phi 2. But notice we can introduce yet another term, which is minus rho over 2, phi 1 square, phi 2 square. Okay, so this field theory would have all kinds of process in it. For example, particle 1. So each of these fields would produce a particle. So particle 1 would scatter into particle 1 plus particle 1. Then particle 2 would scatter into particle 2 into particle, 2 particles. But we can also have 1 plus 1 going into 2 plus 2. And so on. For example, this term could create 2 particles of type 2 and remove 2 particles of type 1. Now, this theory has 5 parameters. Okay, M1, M2, which is the mass of the 2 types of particles, lambda 1, lambda 2, and rho. And so, in general, then there's no relationship between these. If you have 5 arbitrary parameters, then it is completely, there are 5 arbitrary parameters. There's no relationship between any of these processes. Now, just imagine, of course, we don't believe that this is the fundamental Lagrangian of the universe, that the universe is not described by this Lagrangian, but just suppose that the universe is described by this Lagrangian. Then as I said in my popular lecture yesterday, this would be very disturbing. I mean, it could be that we live in a universe like that. But it's almost an article of faith among theoretical physicists, enunciated forcefully by Einstein, among others, that the fundamental laws of nature should be orderly and simple rather than arbitrary and complicated. And this orderliness is reflected in the symmetry or the lack of symmetry in the action. So if we have something like this, there are 5 unknown parameters. So suppose we introduce some symmetries. So in particular, we can introduce a symmetry in which phi 1 and phi 2 are interchanged. We will require that the physics be invariant under this. Okay? So if we do this, then instead of 5 parameters, it's forced that m1 would be equal to m2. The 2 masses would be equal, and lambda 1 would be equal to lambda 2. Okay, so the 2 particles will have the same mass, and their interactions with themselves and with each other would be the same. So this is called an interchange symmetry. Okay, then the world becomes more orderly in the sense of Einstein. But we can even go further. Suppose we now impose, so now we have 3 parameters, right? The masses, the lambda, and rho. But now suppose I impose further that rho is equal to lambda 1 equal to lambda 2. Then we see that these quartic terms, right, the terms that have 4 powers in the field, they become, let me see if I write it down, -1/4 lambda phi 1/4 plus phi 2/4 minus 2, no, plus 2 phi 1 phi 2. So now we see, lo and behold, remembering high school algebra, remember that this is lambda phi 1 squared plus phi 2 squared. So we see that this actually has a much higher symmetry. It's not just interchange of phi 1, phi 2. What is the symmetry? I think most of you can see it. It's namely that phi 1 of x could go into cosine theta phi 1 of x plus sine theta phi 2 of x. Phi 2 of x goes into minus sine theta phi 1 of x plus cosine theta phi 2 of x for arbitrary theta. Oh, yeah, thank you. So there are 2 squares here. Okay. Students, please, those of you who are awake, please be as alert as Professor Johnson, or at least try to be as alert as Professor Johnson. Okay, so where theta is an arbitrary angle, so you recognize that this is actually a rotation in a 2-dimensional space. So in the internal space described by the 2 fields phi 1 and phi 2, there is a rotation symmetry. And this corresponds, to use group theory, the group SO2. So this is an internal symmetry. So as I explained in the popular lecture yesterday, this was a really revolutionary notion. I mean, this is really, and it took a very brilliant young man, who's probably not much older than most of you, namely Werner Heisenberg, in the early 1930s, to realize that there's symmetry in internal space. Okay.
Sorry, Professor.
Yes?
How did that quote change to a half the bottom of that top black board?
Oh, I'm sorry. Yeah, thank you. Here's someone even more alert than Johnson. What are you doing? You are asleep. Clifford, shame on you. Gee. See, there's a professor who can't do arithmetic. In fact, there are 2 of us. And Marov is totally asleep. Okay, so now the important thing to emphasize is what I said here, arbitrary theta. So therefore, this is actually what is called a continuous symmetry. So unfortunately, personally, I really hate jargon, but unfortunately, in any areas of human endeavor, there are always jargons. So we have to learn the jargon. Notice that this symmetry is continuous. On the other hand, this symmetry is called a discrete symmetry. Okay. Now, historically, what Heisenberg did was that he noticed that experimentally at that time, the neutron was discovered by Chadwick. And the neutron happens to have almost the same mass as the proton. So, almost equal. But the two particles are quite different because the proton has electric charge and the neutron not. So Heisenberg said, if I imagine a world in which somehow the charge of the proton disappears, then these two particles are the same. I wonder if there is a rotational SO2 symmetry that connects them. Okay? So this is a baby version of what Heisenberg said. Now, I think it's important. So as I also said in my first lecture, in Santa Barbara and at other universities where I have taught, I've always berated the students for not knowing enough about the history of physics. I think it's important to know about the history of physics and to put things into context so that you can appreciate what the great people have done. Now it's easy for us to say, but I think that just the act of imagining that the proton doesn't have a charge, imagining a universe in which that happens, is highly non-trivial. So continuous symmetry has some very important properties, and which I'm going to now tell you. So let us first look at the equation of motion. Oh, okay. Equation of motion. There's a glare. I realize when I sit on that side of the room that it's not possible to see this. Would it help if this light is turned off, or it would make it worse?
No, I think it's fine. Just the writing was a little small.
Oh, okay. All right. I'll make it larger. So the equation. Sorry?
Okay, it's just me. It's a little small.
Okay. Well, so the equation of motion is equal to del squared plus m squared. Now, let me go slowly, right? Okay. When we have one scalar field, we derive the equation of motion for you, and Professor Smith also wrote down the Euler-Lagrange equation. Now here, we have two fields, so we should introduce the notation phi a, where a is 1 and 2. And we also introduce the notation phi vector is the collection of two fields, phi 1 and phi 2. I'm sorry, I seem to have reverted to a smaller font. So here, we have actually two equations of motion, one for the field phi 1 and one for the field phi 2. So it turns out that this is the equation of motion, where this is phi vector dot square. Okay. Now, so these are the two equations of motion, which I leave as if it's not immediately obvious to you, you should do it as an exercise. So this homework exercise. Now, suppose we stare at these two equations. So these are two equations. If we stare at these two equations long enough, we'll discover something amazing, which is that if we define this current J mu to be I phi 1 d mu phi 2 minus phi 2 d mu phi 1, okay, then we see that d mu J mu is I, well, if I differentiate, there's several terms, but I'll just write down the answer, and you see that. That's the answer, because when the derivative on phi 1 and derivative on phi 2 it cancels. And now we look at this. And now we plug this equation in for del square phi 2. You discover, lo and behold, that this is 0. So this is amazing. We discover that there is a conserved current. Okay? And this conserved current, it tells us that there's a current whose divergence is equal to 0, that the symmetry implies a conserved current. Now, this is actually one of the most profound observations in physics. And I didn't say it was one of the most profound observations in physics. Einstein said it. Einstein was extremely impressed and thought this was incredible. Okay, so students, when they go to the movies, they know when to get excited because there's some background music. But when you lecture students, it's amazing. You tell them the most amazing thing in the universe, and they just sit there like this, right? So I just want to tell you, when Einstein saw this, Einstein thought it was the most amazing thing he's seen. And this connection between a continuous symmetry, so continuous symmetry and conservation law are related. This observation was made by a young woman physicist named Noether. So, and this condition is sometimes known as Noether's theorem. And Noether showed that this occurs in general. And this is a very important part of quantum field theory. Now, just as a side remark, after Noether made this very important observation, Hilbert also thought it was a great discovery and proposed that she get a position at the university. And the university in Germany allowed her a position, but without salary. She's allowed to teach, but with no pay. And Hilbert tried very hard to get her a real job, but the rest of the faculty all refused because of the fact that she is of the rather strange gender at that time. And so the famous story is that Hilbert stormed out of the faculty meeting saying, "Gentlemen, this is a university, not a bathhouse." So Emma Noether then later left for the United States and died in Pennsylvania. Very unfortunate. Okay, now, as is the case, often the case with the most important theorems, the proof of Noether's theorem is astonishingly simple. Okay, so I'm going to now give you the proof. We'll denote the fields in our theory generically by phi A. So in fact, the proof is very, very general. A doesn't have to be run over 1 and 2. A could run over many, many different values. Now, because the symmetry is continuous, we can consider an infinitesimal change. Infinitesimal change, delta phi A. Okay. Yes? Discrete and continuous, yes.
So that it cannot be differentiated, the discrete?
Yeah, exactly. So you see that that's a very good question. Because the symmetry is continuous, we can consider infinitesimal change. So when we have a discrete symmetry in which phi 1 is interchanged phi 2, then you cannot consider infinitesimal change. Phi 1 change into phi 2, phi 2 change into phi 1, and you do it again, phi 2 change back into phi 2, and so on. Okay? But if you have a continuous transformation like this, then this works for arbitrary angle, right? So therefore, if I can do it for very small angles, I can do it for any angle I want, and in fact, I can do it for a very, very small angle. Okay? In which case, delta phi 1 just becomes phi 2 times theta if theta is very, very small, and delta phi 2 is minus theta phi 1. Right? So that was a good question. So that's the difference between discrete symmetry and continuous symmetry. So Noether's theorem, I guess if I pronounce it, if I remember my German from graduate school, only works for continuous symmetry and not for discrete symmetry, because in the proof, we require infinitesimal transformation. Is that clear to everyone? Okay, good. Okay, so consider infinitesimal change delta phi A. Now, by assumption, Lagrangian does not change, right? So therefore, we can write down 0 equal to delta L. But what is the change in delta L? It's delta L, delta phi A, right? Since the Lagrangian depends on the field phi, but it also depends on the derivative of phi. Okay? Sum over A, this notation that I've been using, remember? I said repeated indices are to be sum. So we vary respect to all the fields in the theory and then multiply by the infinitesimal change, and similarly with the derivative. So in fact, the Lagrangian, I guess now I realize these blackboards you have to go, it's better to write horizontally, but too late did I realize this. These are actually very nice blackboards. Marov, you should try to get the department to buy some blackboards like this. No, you are younger. You have more energy to deal with the bureaucracy. Okay, so here's the Lagrangian, and you see that it depends on d mu, right, the derivative of the field. So that's why we have a term like the variation of d mu with phi A. Okay, now this term is just d mu delta phi A. Why is that? Because delta phi A, remember in our simple example, delta phi 1 was just theta phi 2. So theta is independent of x, right? So therefore, the variation in the derivative of phi 1 is just the derivative of the whole thing, right? Since theta is in, okay. So therefore, this is equal to delta L, delta phi A, plus delta L, delta d mu phi A, d mu delta phi A. But now, at this point, we would have been stuck. We just have these two terms. But now we remember something which Professor Smith told you. Namely, the Euler-Lagrange equation of motion which tells us that d mu delta L delta d mu phi is equal to delta L delta phi. Oh, I forgot the index A here. A. Okay? So therefore, one of those terms we can plug in. In fact, we plug in delta L delta phi A. So we plug in delta L delta phi A, this term, as this piece here as d mu. Write it bigger, d mu. Delta L delta d mu phi A times delta phi A. And now we come to Noether's great discovery, is that these two terms combine very nicely into one thing. It combines into d mu delta L delta d mu phi A delta phi A acting on this. Okay? So, since this is equal to 0, we proved that if we define J mu as delta L delta d mu phi A delta phi A, we will get the conservation law. So that proves it. So if we have a continuous symmetry, we get a conserved current. Okay. So this is actually, in general, many different currents because there could be many different transformations. So there could be, in principle, could be many currents, depending on how many different infinitesimal transformations there are. So as a homework exercise, you should check immediately for the case phi 1 and phi 2 that I mentioned. Okay. Are there any questions?
So
Yes?
holds for any continuous symmetry?
I'm sorry?
Is that holds for any continuous symmetry?
Absolutely.
And not for a discrete, like a mirror symmetry?
Right. For discrete symmetry, it doesn't work, but for any continuous symmetry, and it's not just for scalar fields, because there's nothing in this derivation that says phi has to be a scalar. There could be some extra Lorentz indices on the phi field, and it even works if it carries a spinor index. So it works for the electron field, and so on. Okay.
Assume, however, that the symmetry is global so far.
Of course.
It did not depend on
Of course.
the
Yeah.
position.
Of course. Of course. That turns out to be one of the most important questions in the history of physics, the question he just asked. And this was if you read Yang's autobiography, he said he wondered about that when he heard the professors giving this proof. And that was the question that led him later to not be engaged there.
That's the answer.
Yeah. Yes, question? Yes, in the back.
Is the corollary of the theorem true as well?
Sorry?
The corollary of that theorem, is it true?
The reverse of the theorem, let me not answer the question. It's technical. Okay. In general, it may not be. Yeah, question? Oh, yeah, you were asked, you had your hand up.
I think to what extent is
Yeah.
there an inverse result?
Let me go over that. Okay. Yes?
The answer to the question was it also holds for local symmetries, or?
No, it doesn't.
It does not.
Yeah. Well, because it's this step here.
Yeah.
Okay, as I said. Otherwise, you wouldn't be able to place that like that. Okay?
Tony's comment was that when you consider the parameters depend on position, you uncover Yang.
Delta L is not 0. The Lagrangian actually changes. Can you still find a conserved current? Okay? Now, this is maybe a little bit too open-handed, so I'll give you the answer. The answer is, think about this. Suppose the Lagrangian actually changes, but its change is equal to the divergence of something. Then there is still a conserved current. Okay? And this is, in fact, what happens in supersymmetric field theories. Okay. Now, the other thing, I guess now that I have started giving exercise, I might as well give a lot. And so another exercise, which I'd like you to do, which is in the case of the two fields, phi 1 and phi 2 again, remember, now I'm going to introduce a new concept. So far in these lectures, the fields are real because it started when we discussed the field was the vertical displacement of the matrix of the mass points moving up and down. But we can, in fact, introduce complex scalar fields. And in fact, a very simple example is just phi. I can introduce a field. I've defined phi as phi 1 plus I phi 2. Okay? And the exercise is to show that I can write everything in terms of this complex field. So the complex of this is phi conjugate, and this is Hermitian conjugate, which for our purpose here is just the same as complex conjugate. Okay? So we can then the Lagrangian can be written as, to get all the factors of 2 right, is d phi dagger d phi minus m squared phi dagger phi minus lambda phi dagger phi squared. Okay, so this is I haven't numbered all my exercises. This is exercise 4 or 3 or something. Okay. So the homework problem should be handed to Clifford Johnson, or okay. Now, the next exercise, you notice right away, if you write the Lagrangian in this form, you will observe there exists also a continuous symmetry. Okay? And this continuous symmetry is that the field phi can go into e to the I theta phi. If I multiply by a phase, the Lagrangian is left invariant. Okay? So when I was an undergraduate, I took a mathematics course, and the mathematics professor has this term called self-proving theorems. He would write down a theorem, and then he said this is a self-proving theorem because it's so obvious that it proves itself. And so in this course, eventually, in the end, the students realized that every theorem he wrote down was a self-proving theorem. He never gave any proofs. So we just learned a whole bunch of theorem, but we never learned to prove anything. So this is what I would call a self-proving theorem as well, right? But let me tell you how that works, because if phi goes into e to the I theta phi, phi dagger goes into e to the minus I theta phi dagger. So if I look at this Lagrangian, I see every time I have a phi dagger. So the phi, when I transform, gives a factor of e to the I theta. This gives e to the minus I theta, and the two exponential factors kill each other. Okay? So there is a continuous symmetry, and therefore, according to Noether, there should be a conserved current. So the exercise is to show that the current is the same as the current that we obtained before. Okay? So because we just rewritten the theory, it's the same theory, we rewritten in different form, it better be the same. But this complex formulation is very important if next time I get as far as Yang-Mills theory. I'm starting to worry that I may not have enough time to get to Yang-Mills theory. This is very important that when you have complex phases, so this is a complex phase. And if we get to Yang-Mills theory, the complex phase would be, in fact, an element of a group. Okay. How many people, can all those people who do not know anything, who have never heard of group theory, raise their hands? Those who have never heard of group theory. Okay, so one person. Okay, everybody else knows group theory. Good. So because for some version of group theory, so for Yang-Mills theory, I would need to have a notion of group theory. Okay. So now we have yet another very elegant result, which I will perhaps write on. Where should I write this? Because I need the formula for the current. Okay, I need this formula. So the idea is to move horizontally. Sorry? Phi dagger is the complex conjugate for it's actually the Hermitian conjugate if phi is an operator. But because we're doing the path integral formalism, the path integral formalism is very nice because you don't have to deal with operators. It's just integral over fields. But so far, our fields are just real numbers. They're real fields. And now, if I form phi 1 plus phi 2, it becomes a complex number, and dagger is just complex conjugate. So phi dagger, as I've written here, is just phi 1 minus I phi 2. Other questions?
Yes.
Yes.
You were asking about, you were suggesting that some group theory might be needed for the Yang-Mills.
Yeah.
Can you suggest to those who may feel they want to...
You mean learn group theory over the weekend?
Well, not necessarily. Well, what's the minimum requirement? And suggest to those people who are a little rusty that they talk to their friends.
Okay, very good. Very good.
What do they need to know?
Okay, you will need to know about a group called SU2. Okay, So if you don't know what SU2 is, you should go ask Professor Johnson, or go to a library, or ask the other students who know what SU2. Okay, very good. So how many new government? We're getting. Yeah.
The problem is we don't have access to information. We don't have access to the library. The computers, we sit there for 20 minutes, just check now and come back. So after lectures, we simply go and sleep. That's it.
Okay.
It's more of a holiday resort rather than a...
Right, so let's change that.
Yeah, have to open up the library.
So let's change that. I'll inquire about the library issue, but as the primary resource until we sort out the library is each other, as we were talking about earlier. Okay?
And there is access to the internet, so you could probably look
Right.
up on the internet.
Have you tried doing, instead of checking your email or seeing what's going on CNN or what have you, go to Google and type SU2 and see what you get.
Yeah, the problem is that this given us, say, 30 minutes, half of it is tea. When you come from tea, you go there 15 minutes, not enough.
Oh, I see.
And also, if you want to print a paper, there's no.
No, you can drink tea and learn
Just
group
to
theory.
print, if you get a paper.
Yeah. Well, I donated. Well, one.
Okay, that's a wider issue, but
Yeah.
certainly from the point of view of maximizing the time you have in that, there's also lunch time, which I believe is longer than half an hour. So just talk to each other, and I'm pretty sure in half an hour, if the people who say they know what SU2 is genuinely know what it is, I'm pretty sure that in half an hour you can exchange the idea to your colleagues. I don't think we need more than that, and we don't need the web for that. So let's give it a try and see how much we can learn from each other over tea.
Okay.
In that half an hour.
Oh, this is very good. I really applaud this. The other thing is that, well, unfortunately, my books that as you know, I donated some copies of my book for the school, but it has yet to be picked up from customs. And the customs seem to regard quantum field theory as contraband. And so I also say that in my book, there's a whole appendix devoted to group theory for people who don't know anything about group theory.
Maybe we should borrow your copy and photocopy.
Yeah.
With your
Photocopy that?
Yeah.
Oh, okay, sure. Sure, absolutely. Yeah, I waive for copyright. Well, by the way, this book is, if you look in the back, it's endorsed by one Professor Clifford Johnson. That's what he says. He says, buy this book, Clifford Johnson, University of Durham. Okay, so in the 5 minutes left, let me finish another very, very important observation in field theory, but of course more general than field theory, but it's very important, this result, which is that if you have a conserved current, we have a charge, right? So you remember from your course on electromagnetism, the charge is defined as the space integral, and let's just stick to three-dimensional space, but it works in any dimension, of the time component of the current. Okay? Now, the time component of the current, now that I have learned how to raise this up and down, I know how to move horizontally, is right here. So the current is here. So the time component of the current are here. Phi A delta phi A. Okay. So now comes a very important observation that let us calculate the commutator of Q with phi A. And at this point, I realize I am in trouble because I skipped the canonical formulation of quantum field theory, that chapter, because just that's for lack of time. So, and I only developed for you the path integral formalism. I mean, in 2 lectures, there's only so much I can do. So I have to appeal to you to remember your quantum mechanics. So it's just really quantum mechanics. So remember in quantum mechanics, let me do it on the side here very, very quickly. So this is like a 30-second review of quantum mechanics. Remember that if a Lagrangian in quantum mechanics is half mq dot square minus v of q, what did Mr. Heisenberg tell us? Mr. Heisenberg said that the variation of the Lagrangian with respect to the time derivative of q, which is the degree of freedom here, the dynamical variable. I'm running out of time, so it is, Heisenberg tells us that this is the conjugate momentum. And the conjugate momentum has a commutator with q, pq is minus I, right, with h bar set equal to 1. Okay, so here you see exactly the same thing. Aha! Lo and behold, aha! It's one of those aha moments. You see that variation in quantum mechanics, the variation of Lagrangian in respect to dtq is the conjugate momentum. And here is the variation of Lagrangian density with respect to the time derivative of the dynamical variable, which is the field, phi a. So this is the conjugate momentum of the field. So conjugate momentum. And it is, the notation for that is pi a. Okay? So when I do this commutator, I have I integral d3x pi a delta phi. I'm too many a's here, so I call this b. B is summed over, commutator with phi a, right? And now I have the commutator of pi with phi. Since in our example, delta phi is just some linear combination of phi, and phi commutes with itself. So I pick up the commutator between phi a and pi b, which is just minus I delta AB. So therefore, we obtain this amazing result that this is delta phi A. So the charge, as I've written up there, another fundamental result, the charge is the generator of the symmetry. So you see it's a very beautiful circle of ideas to summarize for you in the remaining 1 minute. Is that we have continuous symmetry, we have a conserved current, that was Noether's theorem. When we have a continuous symmetry, we have a conservation law, Noether's theorem. When we have a conservation law, we can write down the charge, and the charge turns out to be just the generator of that symmetry. If you commute the charge of the field, you get the infinitesimal change in the field. Okay, so as Professor Clifford Johnson said, your job is to learn SU2 by Monday, and hopefully we'll get to Yang-Mills theory. I can't promise, but I'll try. Okay.
Just one comment. If you could go to the top of the list.
Yes.
I do think it's worth just commenting. You said it yesterday, but the symmetry you've got there, I think it's worth commenting that is a symmetry between the electric and magnetic fields when there is no current. And I think that's really an important point.
Yes. 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 Yes.
Just about please, is there any practical implication of this conservation of current?
Is there practical conservation?
Implication.
Oh, absolutely. You know, in nature, we know all kinds of things are conserved. For example, electric charge is conserved. The electrons are conserved that if you have, before this lecture, we had 17 electrons in this room. We still have 17 electrons. The number of electrons cannot increase and cannot decrease. And similarly, the number of baryons, the number of protons and neutrons in this room have not changed. And so people, in fact, historically have worked backwards. They observe experimentally a conservation law, and then they ask what symmetry produced this conservation law. Okay, absolutely. Not only applications, but much of fundamental physics is based on that connection. Yes?
Explain that last step you did over there.
Oh, okay. I did go over this a little bit fast. I see what the problem is. Okay, so very good question. Thank you for pointing this out. I went over a little bit too fast. Because I think Clifford really put the sort of whip to us, and we kind of feel a little bit unnerved by the presence of Clifford. So I forgot to tell you something, which is the variation of Q. Yeah, right. So let's say Mara, let's laugh. Q dot, the variation, so remember in quantum mechanics, the variation with respect to Q dot is the conjugate momentum. And so we have this commutation relation. Now, with the variation respect to the field phi A, there's one thing that I glossed over very, very quickly, which is that, in fact, phi A depend on x. So therefore, the conjugate momentum also depend on x. But this is like if I have many degrees of variable, as I explained in the first lecture, there's some extra index here. And so this is actually has x, and this has y. And then this the conjugate commutation relation really holds at so-called equal time. There's some delta function and so on and so forth. Okay, but it's all worked out in detail. I gloss over those technical details. Okay, good.
So just to remind you then, this isn't a holiday camp. Get your coffee, get your tea, and talk to each other. Those of you who did not put your hand up and thus identify yourself as knowing what SU2 is, seek out. So those people who said they didn't know what SU2 is, could they stick their hands up now? Okay, I see a little more than previous. Okay, right? So all of you look around at those hands that are up, and at coffee and tea, seek out those people and talk to each other. By 11 o'clock, everyone should have an idea, at least roughly, what SU2 is.
Because Professor Martin would need it.
Because Professor Martin will need it. Okay? And in the meantime, I will try and look into getting those appendices copy from Tony's book. But don't wait for that. Talk to each other about it. This is serious. That's why we're here.
Sorry, I've just got a question with that thing. I just remember what we learned in quantum mechanics for the momentum. You could write it as an operator.
Yes.
H bar over I grad.
Yes.
Is there a similar kind of thing to this conjugate momentum field?
Yeah. There is, as I said in the first lecture, that there are two, there are really, as you learn in school, there are two formulations of quantum mechanics. There's the Schrödinger formulation and the Heisenberg formulation. So the Heisenberg formulation is in terms of operators. But then there's a third formulation due to Dirac and developed by Feynman called the path integral formalism. And so in the path integral formalism, one advantage of the path integral formalism is that you don't deal with operators. But in the Heisenberg formulation, you do deal with operators. Okay? So in this very compressed course, which cannot even be called a course, I use the path integral formalism because it's the quickest way to get to results in quantum field theory. But on the other hand, there are also some advantages of the canonical formalism. So in my book, after I developed the path integral formalism of quantum field theory, I also talk a little bit about the what is called the canonical formalism, which is sort of the version of Heisenberg's formulation extended to quantum field theory, in which fields are them operators. This thing phi I've been written down becomes an operator, and its conjugate momentum is an operator. And unfortunately, suddenly here, we have to switch to that formalism. Okay? So I don't know if that answers your question. Okay. Yes?
So, do you have time translation invariance? For every symmetry you have a conserved quantity by another theorem. If you have time translation invariance and you have conservation of energy, you have rotational invariance, you have conservation of angular momentum. What about boost invariance? What's the conserved quantity associated to boost invariance?
No, with Lorentz invariance, it's a general. If you have, as you said, if you have rotation invariance, you have the conservation of angular momentum, right?
Sure.
But if you have boosts, no, you.
No. There is a conserved quantity.
Yes.
It doesn't have a useful name. Some people just call it quantity associated with boosting.
Oh.
It's a Lorentz generalization of angular momentum.
Right.
From 3 Euclidean dimensions to 4 space-time dimensions.
I see. Okay.
Yeah. And there may be some old-fashioned name for it, like the moment of momentum or something like that, but it's not something that one deals with very much.
So Jeff is doing what Sidney Coleman used to do at Harvard, which is that at the end of the seminar, Sidney Coleman would just slowly wander in, and then he would ask a penetrating question.
And the quantity that Jeff mentioned tends to come up less often. It, of course, exists in every Lorentz-invariant field theory, but it doesn't come up in many other contexts because once you add anything to the vacuum, it will break Gaussian. Anytime that world line breaks Gaussian.
Okay.